Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Vishal Singh, who will tell us about extendable quantum measurements and limitations on classical communication. So Vishal received integrated MSc degree from the Indian Institute of Technology in Roorkee in 2019, and an MSc degree from the School of Applied Engineering Physics in Cornell in 2024. And he is currently pursuing a PhD degree in Cornell under Mark Wilde. And his research interests are in quantum Shannon theory and quantum resource theories. So Vishal, the floor is yours.
Yeah. Thank you. Thank you for the introduction. Hi, everyone. Today I'm going to present this sort of recent work that we did basically at the end of last year, and this will be presented at ISIT. Unfortunately, I won't be presenting it because I will not be in the US, but Mark will probably present it. So if anybody is there, you guys can see it again. Yeah, this is joint work with one of my colleagues, Teshani, and my supervisor, Mark. And so let's go ahead. I'll just briefly go through like mathematical preliminaries. I'm pretty sure you guys know this stuff, but just to ensure the notation, with a quantum state, I mean a unit trace positive semidefinite operator. With a quantum channel, I mean a completely positive trace preserving map. So basically something like this that acts on a positive semidefinite operator, and the output operator is also positive semidefinite, and it preserves a trace of the operator it acts on. And a POVM is basically a collection of positive semidefinite operators with sum up to identity. And if you perform a measurement, it can be mathematically represented by a POVM, and the probability of obtaining an outcome Y is given by the trace of m times rho. Okay, so extendability is basically an idea that we use to deal with the hard problem of determining if a quantum state is separable or not. So to determine if a state is separable or entangled, it's an NP-hard problem. So what we do is we ask a simpler question: is the state symmetrically extendable? With that, what we mean is that, let's say you have a bipartite state like this. So let's say Alice holds the red dot and Bob holds the blue dot, where each dot represents a qubit, let's say. And the question is, can you extend this state to a tripartite state such that there are two Bobs now, and the marginal of the two systems on the left-hand side is the same as the marginals of the two systems on the right. And when you're asking this question, it's very clear that you can always find such an extension of a separable state. Why is that? So let's say rho is a separable state, then you can always write it in this form where P is a probability distribution and sigma x is a set of states and tau x is another set of states. And so you can symmetrically extend it to a tripartite state such that if you trace out system P prime, I missed a P of x there, so that's a typo. But yeah, if you trace out B prime, you still get rho AB, and if you trace out B, you get the same state that is on rho. So basically, every separable state, you can extend it symmetrically. And so what that means is all the states that satisfy this criteria, you can say that they lie inside this green circle. So the outside circle is a set of all states. The set of separable states is the innermost circle, and the green circle are all states that satisfy this criteria that they can be symmetrically extended. And then you can ask another question, that can you extend it symmetrically to a state with four parties, right? And once again, using the same idea, you can show that every separable state, you can extend it in such a form. And so now you have added extra constraints, and you have even further shrunk the set of states that you're looking for. And so when we ask for a tripartite state, we say that the state is 2 extendable. And if it can also be extended to 4 parties, then we say it's 3 extendable because there are 3 identical systems that you have extended to. And you can keep asking this question for more and more parties. And eventually, like you can say even k going to infinity. And what we know from long ago, from 2002, is basically a bipartite state is separable if and only if it can be extended to arbitrary number of parties, right? So, so this is a different way to approach this hard problem of separability. And the question is it easy to determine if a state is...
Sorry, can I interrupt?
Yes, sure, sure.
I just wanted to ask, like, because you've only considered extending Bob,
Yeah.
but I guess like it really depends. Like, so, like, if you know you can extend Bob, then it's a different question if you wanted to extend Alice.
Yes, it's a different question if you want to
Mm-hmm.
extend Alice.
And you can sort of like try to extend both of them at the same time, right?
Yeah, indeed, that's true.
Mhm.
But for most of the talk, I will only consider extending Bob's system. And indeed, I guess if you extend Alice's system as well, perhaps you can show that it converges faster to the set of separable states. But we know that if we just consider extending Bob's system, then also you converge to the set of separable states with like a at the order of 1 over k. So that's the rate at which you converge to the set of separable states.
Okay.
Okay, so determining k-extendibility of a state, you can actually determine if a state is k-extendable or not using a semidefinite program. So this is one way to determine if a state is k-extendable or not. Basically, what we know, at least I know it from a paper from 2014, I guess, that you can always construct an extension which is Hermitian and trace one. It's just that it might not be positive semidefinite. So if you find an extension which is also positive semidefinite, then you know that the state is k-extendable. And so this SDP basically achieves that. And if you fix the k, the SDP, you can show that it takes of the order of like polynomial in the dimension of the extended operator x, right, which is the dimension of a multiplied by the dimension of b raised to the power k. So you need these many steps to compute this SDP, and so you can say that it is efficiently computable in the dimension of the state. And this is how we are getting rid of this, well, not getting rid, but like finding a way around this NP-hard problem, because now this is something that you can compute in polynomial number of steps. And you can use this idea to actually minimize convex functions over the set of k-extendable states. And so, for example, we often encounter things like the uh, relative entropy of entanglement, right? So you have the relative entropy between a state with respect to the set of all separate with respect to a separable state, and you minimize over all separable states. So indeed, you cannot compute that because it would be NP hard, but you can minimize over the set of k extendable states, and that will give you like an upper bound on the relative entropy of entanglement. Okay, so we can extend this idea to quantum channels as well. So first, let's just go through what is a one-way LOCC channel. And in fact, the extendability of quantum channels will appear as a semi-definite relaxation of the set of one-way LOCC channels. Okay, so a one-way LOCC channel, so we were talking in a bipartite channel setting. So basically what happens is that Alice can apply quantum instrument on her system. So E is basically a quantum instrument that outputs a quantum state on system A prime and a classical variable X. And she sends this classical data to Bob. And based on this X, Bob picks a quantum channel. So he has a set of quantum channels, let's say F with a superscript X. And based on this classical bit or classical dit that he receives from Alice, he picks the channel F. And so this entire operation is what we call a one-way LOCC, where LOCC stands for local operations and classical communication. And one way is because only Alice can send classical data to Bob. Bob cannot send it back to Alice. And the key observations to make here are that Alice's signal to Bob can be duplicated because it's classical data, so it can be copied as many times as we want. And Bob applies a local channel on his state. And so basically, we can simply duplicate Bob's laboratory, similar to what we did with states. So yeah, we can basically symmetrically extend Bob's system. Okay, so we can formally define a k-extendable channel as follows, that let's say n is a k-extendable channel, then there exists a channel which acts on one system of Alice and k systems of Bob, and outputs one system on Alice and k systems of Bob. And what this extension basically does is, if you trace out the extra Bob systems that you have added, you get the original channel n. So that is the first condition. And the second condition says that these additional channel is permutationally, it's covariant under permutation. And so what that would imply is that you can trace out any k minus one Bobs. It doesn't have to be the extra ones that you added. It can be like the first to k minus one, and you would still get the original channel that you had. And in this paper from 2022, what they showed was that these conditions, basically these conditions are SDP conditions as well. You can write them as an SDP, as SDP constraints using the Choi operator of the channels. And it converges to the set of one-way LHC channels as k goes to infinity. But they also needed an extra condition to show this, which I'll talk about in some time. Okay. So why is this?
Sorry to interrupt again.
Yeah, sure.
Just to
Yeah,
check,
sure.
so if you have a k-extendable channel, so that means that the choice state of the k-extendable channel is k-extendable? What's sort of like the precise statement one can make?
So the statement that you said, that is true if we have like a channel, like a point-to-point channel. In that case, we say that it's sufficient to require the k-extendability of the choice state. But in this case, they're not equivalent. So if I have to write these, these constraints, they would not exactly transform to the k-extendability of the choice state.
Okay.
Yeah. Okay. So look at So why are we interested in k-extendable channels? Is when we are looking at something like this, that there are two laboratories. They are connected by a quantum channel, and then we are interested in questions like how many qubits can be transmitted over this channel, or how many private bits can be transmitted over the channel, because as I guess, to the best of my knowledge, one of the most important applications of quantum networks is private communication. And so we're interested in these kind of questions. And you can modify the question a bit and look at different metrics. For example, you can also look at what's the minimum error with which you can send a qubit over this channel. And the extendability of channels, they are helpful in getting efficiently computable bounds on these quantities, because as you can imagine, if we have to find out, for example, like the first question, how many qubits can be transmitted over the channel, we need to optimize over all possible encoding and decoding operations. And that is something that you can actually relate to the problem of separability and show that it's NP hard to compute that. And so we use this idea of extendability of channels to actually simplify the question and obtain upper bounds on these quantities. Um, I will not talk about superchannels in this talk, but you can just imagine them to be like an operation that transforms a channel to a quantum channel. So it's what channels do a quantum state, superchannels do to channels. Okay, so this first question was well, not necessarily answered, but an upper bound was found on this quantity in 2019. We found an upper bound on this on the number of private bits recently that I actually presented in the quantum resources workshop where I met Jello, and and the minimum error this was considered in this paper from 2021. Actually, it's the same paper in which they showed that the set of one value CC channel converges to the set of sorry, the set of k-extendable channels converges to the set of one value CC when k goes to infinity. So probably 2022. Okay, so locally restricted measurements. So what we are trying to do is extend this formalism to measurements, and one might say that measurements are a special form of channels. So why look at them in like why not just use the k-extendibility of channels to do so? And it may be a fair concern, but measurements are a very special class of channels. And so we can find very simple ways to represent them, and we don't have to go to the general formalism to analyze these things. And they are very useful in many of the applications that we consider. So, for example, in real life, many times we are restricted to local measurements only. And so you can consider a situation like this, where there is a telescope on Earth, there's a telescope on some satellite that is orbiting the Earth, so very far away, and we're looking at some faraway planet. And we want to know if there's some interesting phenomena happening, which is emitting some entangled photons, and one of the entangled photons is captured by this satellite and the other one on the in the telescope. So in general, because these are like it would be very hard to have like a joint measurement that could measure both the photons at the same time, but they can measure them independently. And as such, that would not give you anything else because you can never know if they were entangled or not. But you can share the classical data that you get out of it and do some classical post processing, and that might help you actually to figure out if they were entangled or not. So it's not as good as doing a joint measurement, but it's not as bad as just doing local measurements without any classical post processing. So now we ask the question: how confident can we be in differentiating a trivial observation from an interesting phenomena? And people who are in information theory, they might know that I'm going to hint at hypothesis testing. Okay. And a similar scenario can appear in laboratories if you think that that example was very far away from reality. What we can see in a lab is basically, let's say there's some interesting phenomena happening and you're trying to figure out what this phenomena is using some probe state, some probe photon, let's say. And you want to figure out, depending on what this phenomena is, it will apply a channel to your state, and you are basically trying to figure out what channel this is. But let's say that you have some idea what this can be. It's either a channel N that is acting on it or a channel M. So it can be something like you like if there's nothing interesting happening, you know that the channel N is applied. But if something interesting is happening, you know that the channel M is applied. So your null hypothesis would be that nothing interesting is happening. Your state rho is being converted into state N rho. But your alternate hypothesis would be something interesting is happening and the state rho is being converted into M rho. But in when we have the power uh, of quantum technologies, you can actually use entanglement to improve your ability to distinguish between these two channels. You can actually send one share of the entangled state to probe this phenomena, and the other share you just measure separately. Now, indeed, if you had some way to do a joint measurement on both of these shares of the entangled state, then you'll be able to figure out what this channel and what this channel is with very high precision. But it might not be possible to do such joint measurements. Usually your detectors are far apart, and we can only do joint measurements in a very small, um, very close by objects. So once again, you can share your classical outcomes that you get, do some classical post-processing, and try to determine if the channel was N or M. And then once again, from an information theoretic perspective, we are interested in this question that how confidently can we differentiate between the null hypothesis and the alternate hypothesis. Okay. So formally putting this together, we call this problem the locally restricted asymmetric hypothesis testing. So basically, we fix the probability of incorrectly rejecting the null hypothesis. We fix that to be less than epsilon. So we want a measurement such that the probability that we incorrectly reject the null hypothesis is less than epsilon. And we want to ask the question, what's the minimum probability with which we reject the alternate hypothesis? Because of course, if there's something interesting happening, we want to know for sure. If there's something not so interesting happening, then it's okay. So this can be written as an SDP. So let's say rho corresponds to your null hypothesis and sigma corresponds to your alternate hypothesis. Then this is precisely how you would compute the minimum probability of incorrectly rejecting the hypothesis, alternate hypothesis, which is also called the type 2 error. And if you are restricted to local measurements, then you cannot apply any arbitrary lambda that you want. It has to be something that is of the form of a that can be simulated by local operations only. So this would be the type 2 error in that case. So the first thing is easy to compute because it's an SDP, but the second one is hard to compute because once again, the same underlying mathematical structure comes into play that the separability problem is NP hard. So that's why we would want to use the ideas of k-extendibility to figure out what is the minimum type 2 error when you're considering locally restricted measurements. And then there can be many ways of defining locally restricted measurements. The most basic one is where you do local measurements, you get the classical data, and then you do some classical post-processing and get a final outcome that would tell you if it's corresponding to the null hypothesis or the alternate hypothesis. And additionally, what you can have is some sort of shared randomness or common randomness. So based on this random variable that both Alice and Bob draw, they apply some measurement to their individual system. And now they get the classical outcomes and do some post-processing to determine if it was the null hypothesis or the alternate hypothesis. And of course, this gives you a bit more power than just local operations. So LOCR stands for local operations and common randomness. And then finally, what we'll be mostly be concerned about in this talk is one-way LOCC measurements or 1WL. In this, what we kind of model is that Alice does a measurement, gets a classical outcome, and tells this classical outcome to Bob. And then based on this classical outcome, Bob applies the measurement. So he has a certain choice in what measurement he wants to apply, and then tries to determine if it was the null hypothesis or the alternate hypothesis. So in cases where you have a bit of room, where you can hold the qubit for some time and then decide, and based on Alice's outcome, you decide which POVM you want to apply. So that is where this one-way LOCC measurement comes into play. Okay, so extendability of one-way LOCC measurements is like we talked about in channels that you can symmetrically extend Bob's lab. So similar thing, you can do it here. I mean, this is almost the same diagram as k-extendible as one-way LCC channels. So what we can do is copy the data that Alice is sending to Bob and just send it to second Bob, right? And the second Bob has the same strategy to pick the measurements as the original Bob. And so what you get is two classical outcomes, y1 and y2, and you can keep doing this over and over again. And so it will be a symmetrically extended Bob system. Okay, so to put things simply first, let's just talk about two extendable measurements. Okay, so let's say P is a bipartite POVM, then we say that P is two extendable if there exists this tripartite POVM, which gives out two classical outcomes, such that first of all, if we uh, discard one of the outcomes, we retrieve the original POVM. And secondly, if we swap the inputs, it's equivalent to swapping the outputs. So diagrammatically, it's something like this, that basically if you trash one of the outcomes, it's like you simply applied the original POVM to Alice and Bob, and third Bob system, you just discarded it. And the second one is basically if you permute the uh, input systems and permute the output systems. So this is two extendability, so just swapping them. So that is just exactly the same as the original POVM. And then to go to k-extendable measurements, we basically consider the most natural extension is that instead of just trashing one of the outcomes, you trash the extra k minus one outcomes. And what you get is just the original POVM that we're concerned with. And if you apply any permutation to the input systems, that is equivalent to applying a permutation to the output systems as well. And and this is the additional condition uh, which I was talking about that was shown in the case of channels, which led to this convergence to the set of one-way LCC channels. And what it basically says is that let's just ignore Alice's system, and what that means is that it's equivalent to ignoring Alice and one Bob system, and it's like a non-signaling condition. So basically, what this says is that BK cannot signal anything back to any of the other Bobs, right? So, and it can be a question if this condition is actually needed. Mathematically, it's useful in showing the convergence, but physically, it does not look like that it gives you any further intuition, right? Like you can wonder if the first two conditions are enough. So that one might consider still an open problem. That are the first two conditions enough, even in the case of channels, are the first two conditions enough to show that that the set of k-extendable channels converges to the set of one-way LCC channels. So yeah, the additional constraint is just to show the convergence to the set of one-way LCC measurements. And this is another condition that we actually use in practice, which is the partial transpose condition. So the PPT criteria is very famous. It has been used to to get a semi-definite relaxation of the set of separable states as well as a set of LOCC channels. And so we can use this condition here as well. And that uh, possibly gives you a faster convergence to the set of one-way LCC measurements. For simple cases, indeed, it gives you an advantage. It definitely restricts the set of measurements further. But how fast would the set of we call it KPPT extendable measurements? How fast the set of KPPT extendable measurements would converge to the set of one-way LCC measurements? That is something that we need to look at. Okay, so convergence to one-way LCC measurement, like I said, that the set of k-extendable measurements indeed converges to the set of one-way LCC measurements. So So yeah, that is one way to test if a measurement is one value CC or not. You just find out if it is k-extendable for every k. I mean, of course, we can't do it in practice, but in theory, that is what you can do. And what it implies is that if you have a POVM PY, then there exists one velocity POVM QY such that this condition holds. So you see that the probability distribution are very close and they converge at the rate of 1 over square root of k. And the similar thing is true for channels as well. And in fact, what you can show is that um, if you consider k-extendable channels and you demand them to be a channel of the form that takes a quantum input and returns a classical output, you can show that it is equivalent to this k-extendable measurement that we have defined. So that is another sanity check that indeed this is the correct definition that we're looking for. Okay, applications to classical. Can you tell me how much time I have left?
I think you can have like 10 minutes easily.
Okay, okay.
Yeah, but
Okay, I'll try
yeah,
to.
10, 15 minutes is fine. Yeah.
Okay, cool. Thank you. So now I'll just talk about this application to classical communication. This is just one application that we considered in a short paper. So there's this well-known bound from 2014 that tells us that the one-shot classical capacity of a channel is bounded from above by this by the hypothesis testing relative entropy between these two quantities. Basically, in principle, what we're doing is we'll be saying that you're trying to differentiate between the channel that you're given and a channel that is completely useless for classical communication. And the hypothesis testing relative entropy is an upper bound on this quantity, given that you are only allowed local operations as measurements. So clearly, this is the ballpark of what we want to do. We want, and as we know that the set of unvalued measurements contains a set of local operations. So we have this inequality, and basically we can find an upper bound on the one-shot classical capacity by considering the hypothesis testing relative entropy, which is induced by k-extendable measurements. Right? And we eventually find this SDP, which does not look very nice, but indeed we can compute it. We at least personally, I've done it for k equals 2 and 3, but I can't go to k equals 4 because, as you can see, that the SDP scales exponentially with k, which makes it very bad for going to higher k. But indeed, it shows an improvement over the previously best known results. So previously, what people did was consider the relaxation induced by just the PPT criteria. And so we found this example, which it's not a very natural channel, but it's just one channel for which we can see an improvement. The channel is the choice operator of the channel is given. Actually, the choice state of the channel is given at the bottom, and what we see is an actual improvement over the best known bound. And in fact, if you go to k equals 3, it shows an even further improvement. So so yeah, this whole formalism is not useless. At least we see one area where it can be used. And so
Just to clarify, so when you do this calculation, you do the extension on sort of like, oh wait, for channels, then it's clear which you need to extend, right?
Yeah, so we're only extending Bob here.
Yeah.
Actually, we have looked into this problem of extending Alice as well, but it's just that the SDP becomes very large very quickly. Indeed, it does give an advantage over just extending Bob. So definitely that is something that we want to look at, but it's just computationally it becomes very difficult to deal with. Uh, okay, so computing the upper bound efficiently on the n-short classical capacity. And basically, if you want to compute the n-short classical capacity of the channel, which is usually what we are more interested in, right? It's hardly going to be the case that we are just going to use like a single single use of a channel to send up some classical data. Usually, we want to use multiple copies of a channel, encode whatever we want to do into a um, large code, and then send it over these n copies of the channel. And so in that case, you can what one simple way to do is just like consider this expression here, and that is a valid upper bound. But if we just try to compute this, this would be scaling exponentially in the number of copies, and so that is something that in CS terms that would be inefficient. So but we can see that the right hand side is invariant under permutation of the n copies. So I can just, it doesn't matter what's the order of the channels because they're all the same, right? So what it implies is that the POVM that actually minimizes the hypothesis relative entropy, that we can restrict it to be invariant under such permutations as well. And this this reduction, it restricts the space of all BOVMs that we have to search over from exponential to polynomial in the dimension of the channels, the input and output dimension of the channel. And then we know that there exist some methods to reduce this SDP efficiently. And this was discussed in terms of this uh, hash relative entropy in this paper by Fawzi et al. And we basically use their methodology to see if we can um, reduce our SDP into a polynomial, into something that is polynomial in n. And indeed, it can be reduced, but it becomes much, much worse. It's not quite a bilinear program. Sorry, it's not quite a linear program because there are still some operators in there, but it's very close to a linear program actually. And what we see is basically the parameters of interest are the ones listed at the bottom, this MA, MX, TX, and TB, and they're all polynomial in the dimension, polynomial in n, but like super exponential in k. So it scales very badly with k, but it scales polynomial in n. So we can like officially say that it's efficiently computable in n, right? I have not personally implemented this program yet. It's just a proof of concept, but we want to do it soon. Maybe when I have a bit of time with me. But I did ask Fawzi about if they have implemented this program and if they see improvement. And it turns out in their case, the improvement was like without this reduction, they could go to n equals 2 or 3. But with this reduction, they could go up to n equals 6 or 7, something like that. So at the current stage of computers, perhaps it's not something that gives you some groundbreaking results, but indeed it does reduce the problem from being exponential in n to polynomial in n. So if you have fast enough computers, this method can give you an exponential advantage. And then the big question is, can we obtain an SDP which can be solved in polynomial in n as well as polynomial in k? And why we believe so is that there are a lot of symmetries in K as well, right? So maybe I can just go back to the STP here. So if you see that equation 24, that shows that you can pick something that is highly permutationally invariant. this Q that we're talking about. And yeah, so that would be idea to reduce the dimension in K as well. But in equation 28, that is basically, it does not, the equation 28 is kind of obstruction to that approach. And right now we don't have a way to actually reduce it to polynomial in K. And the question is, that are there any other approaches with which we can reduce it? Because that, I guess, would be a pretty big thing, in theory at least, because of this fast convergence to the set of local operations. Okay, so what we did till now was just consider one-way LOCC operations, but indeed what we want is to converge to measurements that are simulable by local operations only. And at least for this case, like in other cases, one-way LOCC might be useful, but in this case, we actually want to converge to the set of LO. And in this paper from 2018 by Xin Wang, what they did was they introduced a non-signaling condition, and it actually improved the one-shot classical capacity bound for many channels. And in fact, we can simply import their condition in our code as well, and that then becomes a stronger bound. And basically, what we can then claim is that it is indeed strictly better than the bound from Xin Wang's paper as well as previous papers. And then what Jell was talking about, like we can extend both Alice and Bob system, and that is one way to impose non-signaling condition from Alice to Bob. And we call it k-extendibility because it's like you can extend Alice's system to k-Alice's and Bob's system to L-Bob's, and you can play around with what ideal parameters you can choose. I think what we can do on our computers is just that we can set k equals 2 and L equals 2, and the dimension of Alice and Bob to be 3. That is the best we can do. So indeed, it's very restrictive, but it does outperform the bound that we get from 3 extendibility actually. So if there are ways to use some sort of symmetries to further optimize this program, that would be very nice. And then the question is that with the scale extendibility, can we actually prove that the set of k-extendible measurements converges to the set of measurements that are simulable by just local operations? Okay, so that's the end of my talk. Just to recap, what I talked about is that that extendability, it provides a hierarchy of relaxations for optimization of a set of separable states, optimization of a set of one-way LOCC channels, and one-way LOCC measurements. And it leads to efficiently computable bounds on many quantities that we're interested in, especially when it involves something like local operations and one-way classical communication. And they are very useful in analyzing fundamental limits on quantum information processing, such as hypothesis testing with local measurements, which is basically the fundamental that we used for the one-shot classical capacity results. And the future works that we're interested in is basically systematically investigate the scale extendability, and I think optimizing it would be the biggest challenge. But other than that, even if we have some proof of concept, that would be nice. And there are several areas where we can apply this formalism of k-extendibility, k-extendable measurements. In data hiding, what we usually do is basically you try to hide some data in a bipartite state or multipartite state, such that if you only have access to local operations, you cannot retrieve the data. But if you have joint measurements, you can retrieve the data, and that is kind of the idea of local differential privacy as well. So with the k-extendable measurements, you can give information theoretic bounds on how well you can hide data using such techniques. You can find some bounds on circuit cutting and circuit knitting problems. I guess they are a bit of quite popular these days, but it might be that people are just interested in lower bounds, and with this idea of k-extendibility, you'll get upper bounds. So might be a question how useful it is, but indeed it is something that you can apply to. And a particular example that we were interested in is this long baseline interferometry. This idea was, I guess, proposed in 2008, if I'm not wrong, in a paper by Daniel Gottesman. And basically, the idea is that if you have two telescopes very far apart, you can use interferometry, and that would greatly enhance uh, the clarity of the picture that you are trying to capture. And this interferometry is not very easy to do because you need to like send these photons without any kind of decoherence through this very long through this very large distance. But if you have entangled photons shared between these two telescopes, then you can just use the teleportation protocol, and that would simply give you that would simply uh, simulate the whole thing of doing the interferometry. And with these, with the k-extendable measurements, what we're interested in is that if you don't exactly have maximally entangled state, probably using the teleportation protocol would not be ideal. So um, the question is, what is the best you can do in that case? And that is where these ideas of k-extendability are very useful. And so that is one particular approach that we would like to investigate. And then finally, can we efficiently compute the STP with respect to the parameter k? So that is like obviously the biggest question that we would like to answer. So that is it. Thank you for your attention.
Okay, thank you very much. That was a splendid talk. So if anyone has questions, feel free to just mute yourself and ask them now.
Can I just ask, do you mind commenting a little bit more on this circuit cutting and knitting and what you mean by this can provide upper bounds? Like what do you mean?
Yeah.
What do we bounding? What are we upper or lower bounding, and how does this provide upper bound?
Yeah, so in circuit cutting problems, we are often interested in the number of, let's say, rounds that we need to do. So basically, if we try to write any unitary that we want to perform on a quantum computer in terms of in terms of unitaries that can be realized by local operations or one-way LCC operations. And of course, you cannot do it like you cannot write a convex combination of these programs, but you can actually write a linear combination of one-way LCC operators. And so the idea is what people are interested in is this the number of times you need to sample from this probability distribution that is induced by such a linear combination. And so if we, instead of writing it as a linear combination of one-way LCC measurements, you write it as a linear combination of k-extendable measurements. So that will give you basically a lower bound actually on how many times you need to sample from this probability distribution that you have realized using this linear combination. And I guess maybe I said the opposite thing, that we get a lower bound using using the idea of k-extendibility. I don't know if I made it clear. Maybe if I
Great.
draw diagrams.
Yeah,
sure.
Right. Anyone else wants to ask questions? Maybe I have one quick question. So So when you in this plot that you've shown,
Yeah.
I was just curious, like how sort of like how long does it take you to do this kind of calculation?
For I think for 3 extendability, it took me like each point would be like 60 seconds, I think. That was it.
Okay.
But for 2 extendability for this particular plot, I think it was everything was within 2 seconds, I guess. Like finding each point was within 2 seconds.
Okay, so that's not too bad. Yeah,
Yeah,
I was just
yeah,
wondering, like, but of course, like, I guess like it scales very badly, or
yeah,
or
exactly.
the issue is probably you have more like memory issues rather than
Um,
computational time issues.
yeah, I guess memory issues as well. Yeah, if I would go to k equals 4, I think at least MATLAB would just give up because it would require very large matrices. But I would assume that even if we have very large memory, then also it's going to take a long time because it's like scaling exponentially with k.